Hey guys, I hope that you have a really good day today. I really miss you guys so much. I wish that I could be there instead of being here right now. You have no idea. The last thing that we left off with was Newton's first law, as well as talking about inertia. I want to go back and review your notes just a little bit from what we took on, oh my gosh. I didn't get to see you yesterday, and I didn't get to see you on Tuesday. Ugh, it's been too long. Okay, so let's go back and just talk a little bit about just that a force is anything that is capable of changing an object's state of motion. And remember, that just means that it's changing its velocity. So if we're changing velocity in a specific time interval, then we know we have some type of acceleration. So if we have an acceleration, then that means that a force is being applied, and really a force is just something that is capable of changing an object's state of motion. Doesn't mean that it's going to, because there may be other forces that are acting on it that keep it balanced, okay? Or there could be a force acting on it that will prevent it from being moved, like friction, for example. Now, we talked about an idea of a force that's called the net force, and the net force is the sum of all of the forces that are acting on an object. So if I have a book resting on a table, I know that it has two forces acting on it. I have the normal force, which is the force of the table pushing up on the book, and then I also have the weight of the book, or the force of gravity, which is that book acting down on the table, okay? We said that there are two categories of forces. There's contact force and there's a field force. Contact is where you have to have a physical contact between two forces, and then your field forces would be or you could call a field force also an at a distance force, and I don't think we said that last time, so let's make sure that you add that a field force is also called at a distance forces. You may hear that. And those are just going to act over some type of empty space or over some amount of space. So magnetic force would be an example, electrostatic force, which is that big thing, Coulomb's law or Coulombic attraction, and also gravitational force or gravitational pull would be another example. We are going to get into free body diagrams today. I'm going to have you do several examples with free body diagrams. Remember that Galileo is a person that coins or the term or the concept of inertia. We said that inertia is the natural tendency of an object to maintain either a state of rest or to remain in motion. So we said that a mass is going to be a quantitative measure of inertia. So the more massive an object, the more resistance to motion that it's going to have versus the more inertia that it's going to have. So it is in an object's nature to resist a change in motion or to resist a change in velocity. Things do not seek some type of natural state of rest like Aristotle maybe once thought. So we left off, maybe we left off here, maybe we got further, I don't know. Okay, so Newton's first law, a body at rest will remain at rest, or a body in motion will stay in motion unless it's acted upon by some outside force. So you're going to hear key phrases like constant velocity, or you're going to hear a key word at rest. And if that's the case, then the net force is going to be equal to 0. Okay, this is where I want to start off, and let's just talk about mass versus weight. So mass is the property of an object that specifies how much resistance an object exhibits to changes in velocity. In other words, we're saying that mass is just a measure of inertia. So how much resistance an object is going to show if it's about to change in its velocity, so inertia. Masses can be defined in terms of their accelerations that are produced by some type of force that's acting on them. So I have this thing here that a ratio of masses is proportional to a ratio of accelerations. But what does that mean, and how did I get this? So let's talk about that. Okay, so we have seen experiments show us that the greater the mass of an object, the less the object is going to accelerate under some given or applied force, okay? I don't have an active Inspire open, I'm sorry. Not really with it right now. Everyone can enjoy the unicorn pooping a rainbow, thanks to Lulu. Sorry, guys. Okay, so again, we said that experiments show that the greater the mass of an object, the less that the object will accelerate under the action of some given applied force. So that means if I have a large mass and a small acceleration, then they're inversely related or inversely proportional. So let's say that I have some applied force is going to be equal to the mass. I apply some force on a given mass, and that mass has some type of acceleration. So I'm going to call that M1A1, just representing that I'm talking about one particular object, okay? Actually, I'm going to take away that one, because I'm just going to say it's some applied force. Let's say that I apply the same force, but to a different mass. So the same force is being applied to a different mass. I'm going to call that mass 2, and then that's going to have some type of acceleration, which I'm going to call A sub 2. Okay, since these are the same force, I can set them equal to each other. So M1 times the acceleration of the first one is equal to the second mass times the acceleration of the second one. So I just want to see what the ratios of the masses are in comparison to the ratio of the acceleration. So if I divide this side by M2, then I'm going to get M1 over M2 times A1 equals A2. But I want to get A1 over here, so if I do that, it would just be A2 over A1. So I'm showing you this because M1 over here is in the numerator, but A1 over here is in the denominator. It's showing you that they have some type of inverse relationship. They are inversely proportional, okay? So the magnitude of the acceleration that acts on an object due to some given or applied force will show that they are inversely proportional to masses. So acceleration and mass are inversely proportional. Okay, so mass versus weight. I think that oftentimes we think about weight and mass being the same thing because when you take your weight, you think you're taking or finding your mass. But they're actually two different quantities, and you know this by now. So mass is an inherent property of an object. I'm not going to be able to change the mass of an object unless you actually lose some amount of mass, like a limb. Mass is independent of an object's surroundings versus weight that's not. It's dependent on the gravitational force that's applied. And we know that mass is a scalar quantity. It is just a number. So it kind of just obeys like normal rules of arithmetic. And mass is measured in kilograms. That's the standard SI unit for mass. Weight is different. Weight is a vector quantity because weight is it has magnitude and it has direction. And it has a direction because it's actually a force. So weight is equal to the magnitude of the gravitational force exerted on the object. We know that weight varies with location. Our acceleration due to gravity on Earth is not constant. It is not 9.8 meters per second squared everywhere. So it's going to vary with where we're located, even here on Earth a little bit. But for the most part, when we say weight will vary with location, we mean like here versus the moon versus Jupiter. So right now, let's just always assume that we are on Earth. If we looked at an example, maybe our weight on Earth is 180 pounds. Our weight on the moon is going to be 30 pounds because it's, I don't have as much of a gravitational attraction for myself on the moon. But if I look at the mass for me on the Earth versus the mass of me on the moon, 2 kilograms. So mass doesn't change no matter where you are. It is an inherent property of the object, and it is independent of the object's surroundings. But that's different from weight because it is a vector quantity and it is dependent on specifically that acceleration due to gravity, and it's always going to be directed downward toward the center of the Earth. So that gets us into Newton's second law of motion, which Newton's second law of motion is just, of course, the formula that we're going to see so much of in this particular chapter and next chapter. You're going to love it. So experiments show that the acceleration of an object is directly proportional to the force and inversely proportional to its mass. So we constantly think about Newton's second law as being the force is equal to mass times acceleration. I want to point out, it is not just one force, it is all of the forces. So sigma is just representing sum. So it's the sum of the forces. Another way or another name that I could use there would be net force. So maybe instead of writing the sum of the forces and then writing that sigma, instead I could write F net equals m times a. So you'll probably see that more frequently than not. So F net equals m times a. This is fine if you know it that way, but more often than not, you're going to see Newton's second law written like acceleration is equal or proportional to the net force over the mass. And that's just because usually we think about what's happening to the acceleration of an object if we double mass, or what's going to happen to the acceleration of the object if I quadruple the force. So let's actually talk about that. If I quadruple force here, that means I'm going to quadruple the acceleration. But if I quadruple the mass, that means the acceleration will now be affected by, it will be a fourth. So they could ask you any kind of question like that because they'll probably try to do it without so much of the math. Okay, so it shows us the acceleration of an object directly proportional to force, inversely proportional to mass. The direction of acceleration is going to be in the direction of the applied net force. So if I know what all of the forces are that are acting on an object, whatever direction the net force is in, that's the direction that the acceleration will go. And that makes sense. If I'm pushing a box towards the west, I'm going to be accelerating toward the west because the net force is going to be directed in that way. And the only reason that I have that force is because of that acceleration, okay? Units of force are called newtons. We have seen that before. 1 newton is equal to a kilogram meter per second squared. If we're thinking about it in the English units, then it would be a pound, and then a pound is equal to a slug foot per second squared, okay? If we want to go and look or figure out what our weight would be, then weight is what we would symbolize with a lowercase w, or we could symbolize it with a capital F and then a subscript g, just meaning gravitational force or gravitational attraction, okay? And gravitational force, or any force we know is equal to mass times acceleration. So if I'm just thinking about our weight force, then it's going to be equal to mass times the acceleration due to gravity, which is what we symbolize as g. So if I want to find my weight, I'd take my mass times 9.81, and then I would find my weight. And that would be my weight in newtons, not my weight in pounds. Our weight in newtons is going to be a lot more, unfortunately, than our weight in pounds. So gravitational force is always going to be directed toward the center of Earth. So for us, it's always just directed down.